Welcome back, everyone, to another deep dive. Today, we'll be exploring a paper titled Global Convergence and Rich Feature Learning in L-Layer Infinite Width Neural Networks under P Parameterization. Quite a mouthful, huh?
Definitely a title that grabs your attention.
Right. So at the heart of this, this paper really dives into a question that's been kind of central to understanding deep learning.
Yeah.
Can we have our cake and eat it too? Can we have deep neural networks that learn really, really powerful features, like really capture the essence of the data?
Good use of it.
Exactly. While also having some solid guarantees that, like, when we train these networks, the process actually finds a good solution. Like, it doesn't get stuck in some weird corner of the mathematical landscape.
It's a fundamental challenge in machine learning theory, isn't it?
Yeah.
We want our models to both learn complex representations and be reliable in their optimization process.
Yeah. So we want the creative freedom of an artist, but with like the precision of an engineer. And historically, these two desires have often been, at odds in theoretical work.
Absolutely. And this paper is tackling this head on. It's getting at the core of why deep learning is so powerful, but also why it's been so difficult to fully grasp theoretically.
So right off the bat, the paper's main contribution is really exciting. It shows that using a specific way of setting up the network, that they call it maximal update parameterization, or MEP for short, we can actually achieve both rich feature learning, which means the features actually change and evolve during training. They're not just stuck at their initial random value.
They're not just sitting there.
Right. And A&D, we get global convergence, meaning if the training process converges, it's guaranteed to have found a solution that's like truly optimal, a global minimum, not just, some local bump in the landscape.
Yeah, it's not settling for the nearest hilltop, it's finding the highest peak. It's a big deal.
Huge. Now, to understand this, it's helpful to briefly step back and look at where this paper fits into the bigger picture of deep learning theory. So for a long time, researchers have been studying these things called infinitely wide neural networks. And essentially the idea is that theoretically, if you just keep making a network wider and wider, certain properties become easier to analyze mathematically. Like, it simplifies the math, but it can still give you insights into how really large networks behave in the real world.
Yeah, it's like creating a theoretical sandbox where some of the complexities of finite networks kind of fade away and you can see the fundamental dynamics more clearly.
Exactly. And one of the earlier big breakthroughs in this infinite width world was something called the Neural Tangent Kernel, or NTK. And NTK was cool because it provided a way to prove that training these networks would converge to a solution. It gave us that mathematical guarantee, which was huge at the time.
It was a big step towards taming the wild west of deep learning optimization. But like any good story, there's a twist.
Always a twist, right? So the catch with NTK was that the features learned by the network basically stayed really close to their initial random values. They didn't change much during training, and this didn't really match up with what we were seeing in practice.
Because in practice, we see networks learning very specific, hierarchical representations of data. The features evolve to become meaningful and relevant to the task at hand.
Yeah, totally. It's like if you have a chef who can only slightly rearrange ingredients without, actually cooking or transforming them, you're not going to get a very interesting meal, right?
Definitely missing the culinary magic there. And that's one of the key things this new paper is trying to address. How do we get that transformation, that true learning of meaningful features, while still having some guarantees about the optimization process?
Right. So getting into the nitty-gritty, this paper looks at how these infinitely wide networks behave when trained with stochastic gradient descent, or SGD, which is kind of like the workhorse algorithm for training deep learning models.
Yeah, SGD is like the engine that drives the learning process. And they specifically look at how SGD works under this special OMP setup.
And what they find is really cool. Under P, these networks learn features that are not only linearly independent, which means they each capture a unique aspect of the data, like different spices in a recipe, each contributing their own distinct flavor, but these features also undergo significant changes from their initial random state. They actually learn and evolve, and that's what they mean by rich feature learning.
Like the spices are not only distinct, but they're also being transformed and combined in interesting ways during cooking, creating a much richer flavor profile.
I love that analogy. So the paper goes deep into the mathematical weeds, showing how this OMP setup, combined with certain properties of the activation function, which is the nonlinear part of a neuron, it's what gives neural networks, their expressive power leads to this rich feature learning.
The activation function is like the secret ingredient that allows the network to learn nonlinear patterns to capture the complexities of the real world.
Exactly. And the whole analysis is based on some really cool math involving Gaussian processes, which are these powerful tools for modeling random variables. It gets pretty technical, but the bottom line is they show that the features in these networks don't collapse or become redundant. They stay diverse and informative throughout the training process.
It's like ensuring that each spice in your recipe retains its unique character, even as they blend together to create a more complex overall flavor.
Perfect. Now, to really understand how they build their argument, let's walk through the paper section by section. They start with an introduction, setting the stage for why this research is important.
Right. The introduction acknowledges that deep learning has been incredibly successful in practice, but it also points out the ongoing theoretical challenge of explaining this success. Deep neural networks are notoriously complex, and the optimization process involved in training them is highly non-convex, meaning it's full of these hills and valleys that can make it tricky to guarantee you'll find the best solution.
Yeah, like trying to find the lowest point in a super bumpy landscape while blindfolded.
Exactly. And the authors highlight that the vast number of parameters in modern deep learning models further complicates the theoretical analysis.
So basically, the introduction sets up this tension between the undeniable empirical success of deep learning and the difficulty of providing a solid theoretical explanation for it. And this is where the idea of studying infinitely wide neural networks comes in as a way to simplify the analysis while still capturing some of the key behaviors we see in real-world finite width networks.
It's like creating a simplified model of a complex system. We're not trying to perfectly replicate reality, but rather capture the essential dynamics that drive the system's behavior.
And they directly address the limitations of those earlier influential theories, like the NTK that we talked about before. They acknowledge that NTK provided valuable insights into convergence, but emphasize its shortcomings in explaining the rich feature learning that we observe in practice.
It's about understanding the limitations of the map we've been using so we can create a more accurate one.
And they pose this central question. Can we develop a theory that captures both significant feature learning and guaranteed convergence? And their answer, spoiler alert, is yes, through P. They also touch upon why other common parameterization approaches, like standard parameterization, SP, and mean field parameterization, struggle with either not learning enough or suffering from what's called feature collapse, where the features become too similar and lose their representational power.
Feature collapse is like having all your spices suddenly taste the same.
Yeah.
You lose the richness and complexity that makes the dish interesting.
Exactly. They end the introduction by outlining their key contributions, which we've already touched on, showing the simultaneous feature learning and convergence under P, explaining their proof techniques, and mentioning their experimental validation. They also introduce all the mathematical symbols they'll be using, which is essential for anyone who wants to dive into the detailed proofs in the later sections.
It's like providing the glossary of terms before diving into the main story.
Next up, they have the related work section, which is where they place their contribution within the existing landscape of research in deep learning theory. It's like saying, hey, here's where we fit into the larger conversation. And they delve deeper into those earlier theories, particularly the NTK parameterization, giving credit where it's due, but again, emphasizing its limitations regarding feature learning. And they cite a bunch of key papers, giving us a roadmap of how the field has progressed.
It's like showing us the genealogy of the research, how it builds upon and extends previous work.
And they discuss mean field analysis, which was another influential approach that worked well for analyzing shallow networks, but ran into trouble with deeper architectures, where features and gradients could effectively vanish, preventing effective learning. They also mention integrable parameterization as an attempt to address some of these issues, but it still falls short of achieving both deep learning and rich feature evolution.
It's like saying, we've tried different paths, but they haven't quite led us to the destination we're seeking.
Yeah. And then they introduce this idea of tensor programs, or TPs, as a more unified and powerful framework for analyzing the behavior of these infinitely wide neural networks. And within this TK framework, they focus on EP, highlighting its potential for enabling maximal feature learning. They reference a bunch of research that has explored different training regimes, some where the network acts more like a fixed function, and others where it genuinely learns from the data. And they even mention more recent work that uses spectral analysis to study these dynamics in greater detail. And importantly, they provide experimental evidence showing that, unlike SP and IP, which have those limitations we discussed, AP does indeed achieve both significant feature change and diversity. They have some nice figures and tables in the paper that illustrate this.
It's always good to have both theoretical arguments and experimental validation to support a claim. It strengthens the case significantly.
Definitely. Next up is the preliminary section, which lays the groundwork for their theoretical analysis. They start by presenting a table that compares different parameterization schemes in terms of how they initialize the network's weights, the initial variance, and how quickly those weights are updated during training, the learning rate. And they show how these values differ for the input layer, the hidden layers, and the output layer. And these scaling choices turn out to be really important in determining how the network behaves, especially as it gets infinitely wide.
It's like fine-tuning the settings of a complex machine to achieve a specific outcome. The initial conditions and the rate of change can dramatically affect the final result.
And then they formally define what they mean by a multi-layer perceptron, or MLP, which is the specific type of neural network architecture they're analyzing. It's like making sure everyone understands the blueprint of the building they're about to explore.
A shared understanding of the basic structure is essential.
And they highlight this key point. P is designed to maximize the updates to the network's parameters right from the start of training. So, unlike other schemes where things might change slowly, P is all about making those big initial adjustments. And this turns out to be crucial for achieving that rich feature learning thereafter.
It's like taking a bold first step instead of cautiously tiptoeing into the unknown. It sets the stage for more significant changes to follow.
Then they introduce this really clever theoretical tool representing the hidden states of the network, which is like the information that's being passed between layers using something called Z random variables. And this is a way to capture the statistical properties of the network as its width grows infinitely large. Instead of tracking every single connection, which would be impossible, these Z variables allow them to analyze the overall distributions and correlations of the signals flowing through the network.
Yeah, it's like looking at the overall patterns of traffic flow on a highway instead of trying to track every single car individually. You get a more holistic understanding of the system's behavior.
Great analogy. And they formally define the error signal, which is basically how wrong the network's predictions are. This is what drives the training process. The network tries to minimize this error, and the way it does that is by adjusting its weights based on this error signal.
The error signal is like a feedback mechanism telling the network, hey, you're off track here, adjust your parameters in this direction to improve your predictions.
And they walk us through how data flows through the network, the forward pass, and how the error signal is used to update the weights, the backward pass, but they do this in this infinite width limit using those Z variables to describe the process. And there's even a note explaining how this error signal concept can be generalized to different types of learning tasks, like binary classification, where you're trying to classify things into two categories.
It's good to see that they're not just focusing on one specific type of problem, but rather trying to develop a theory that's more broadly applicable.
Now, getting to the heart of the matter, the main results section is where they lay out their main findings. And they start by stating the key assumptions they're making, which are like the ground rules for their theoretical analysis.
Right. Assumptions are important because they clarify the boundaries of the theory. They're like saying, we're focusing on this specific type of scenario, and within these boundaries, here's what we can prove.
One assumption is about the input data, ensuring it's sufficiently diverse and not too degenerate, which is something that's likely to hold for most real-world data sets. The other key assumption is about the activation function.
Ah, yes, the activation function. Remember how we talked about it being the secret ingredient that gives neural networks their expressive power? Well, it turns out that not all activation functions are created equal.
Right, and this is where they introduce this really important concept of a good activation function. And a good activation function is one that has certain mathematical properties that make it well-behaved within their theoretical framework. It ensures that the network can learn complex relationships without collapsing into a trivial or degenerate state.
It's like saying we need an activation function that can spice things up without overwhelming the dish.
And they list these properties, like being smooth, having limited changes in its rate of change, and satisfying this formal definition of a good function. And they mention that a bunch of common activation functions like sigmoid, tan, and psi meet these criteria. So they're not just making this up, it's grounded in the functions we actually use in practice.
It's always reassuring when theory aligns with practice. It gives us more confidence in the applicability of the findings.
And then, drumroll please, they present their main theorem. Theorem 4.5, which is the central result of the paper. It states that under these assumptions, the features learned in each layer of an infinitely wide MLP, when trained with gradient descent under OMB, will always be non-degenerate at any point in time during training.
Non-degenerate features. That sounds important. What exactly does that mean?
It essentially means that the features capture distinct and independent aspects of the data. They don't become redundant or collapse into a lower dimensional space. It's like ensuring that each feature is contributing something unique to the overall representation.
So it's like those distinct spices in our recipe, each one adding its own unique flavor to the dish. No redundancy, no collapse, just a rich and diverse blend of information.
Perfect analogy. And this non-degeneracy has a really important consequence, which they state in Corollary 4.6. If the training process ever reaches a point where the weights stop changing, meaning it has converged, then the error signal must be 0 for all subsequent training examples. In simpler terms, the network only stops learning when it has achieved perfect accuracy, a global minimum of the error.
So it's not just settling for a decent solution, it's finding the absolute best one. That's a pretty strong guarantee.
And it's all thanks to this OMP setup and those good activation functions, ensuring that the features remain diverse and informative throughout the entire training process.
It's like setting the stage for success from the very beginning and then providing the right ingredients for the network to learn and thrive.
Now, the next section, Key Techniques and Analysis, is where they go deeper into how they prove these results. And they start by highlighting 2 main technical challenges they had to overcome. The first challenge was this tension between allowing the features to evolve significantly during training, which is essential for learning, and maintaining a stable optimization process that actually converges to a good solution. In those earlier theories like NTK, stability was achieved by limiting feature change, but that came at the cost of limiting learning capacity.
It's like being afraid to add too much spice to the dish because you might accidentally ruin it. But without enough spice, the dish might end up bland and uninteresting.
Exactly. So they had to find a way to allow for significant feature change without sacrificing stability. The second challenge was dealing with the interconnectedness of the different layers in a deep neural network. Any change in one layer can have ripple effects throughout the entire network, both during the forward pass when making predictions and during the backward pass when updating the weights based on the error signal.
Yeah, deep neural networks are like complex ecosystems. Every part is interconnected, and a small change in one place can have cascading effects throughout the entire system.
And their solution to these challenges involves a clever analysis of what they call structural invariants that are preserved by the Gaussian processes that emerge in this infinite width limit. It's a bit technical, but essentially, while the specific values of the features might be changing a lot, certain statistical relationships between them remain consistent across layers and throughout training. And this preservation of structure amidst change is what allows for both rich feature learning and stable convergence.
It's like saying, even though the spices are transforming and blending, the overall balance of flavors remains harmonious throughout the cooking process.
I love how you keep coming back to the food analogy. It's so perfect. So they go on to explain this Gaussian process view in more detail. Essentially, in this theoretical infinite width world, the training process induces 2 families of Gaussian processes, one that describes how features flow forward through the network, and another that describes how gradients flow backward.
It's like having 2 different lenses through which to view the same underlying phenomenon. The forward lens shows us how information is processed, and the backward lens shows us how the network learns from its mistakes.
And their key insight is that these 2 processes, while seemingly distinct, are deeply intertwined. They show that these Gaussian processes maintain certain covariance properties throughout training. Even as the features are being updated, the statistical relationships between them follow consistent patterns across layers. It's like the underlying geometry of the feature space remains well behaved, even though the specific points within that space are constantly moving as the network learns.
It's like saying, even though the individual dancers are moving freely, the overall choreography of the dance remains intact.
Another beautiful analogy. And this preservation of covariance is what ultimately guarantees that the features remain non-degenerate, meaning they capture distinct information and don't collapse. They explicitly contrast this with the behavior under NTK, where features don't learn as much and eventually become degenerate. They even show some empirical results in Figure 2 of the paper demonstrating that 8P maintains higher feature diversity compared to other parametrization methods.
So they're showing that their theory not only makes sense mathematically, but also has measurable consequences in practice. That's a powerful combination.
Absolutely. Now, to rigorously prove all of this, they introduced this framework they call the evolution framework, which uses this two-level filtration to track how information flows through the network during training. It's like a bookkeeping system that allows them to precisely analyze each step of the process.
A systematic approach is essential when dealing with such complex systems. You need a way to keep track of all the moving parts.
And using this framework, they break down the proof of non-degeneracy into 4 logical steps, each step building upon the previous one. And they carefully analyze how new information is incorporated at each step, showing that this doesn't disrupt the non-degeneracy property.
It's like building a house brick by brick, ensuring that each new addition strengthens the overall structure.
And the good property of the activation function plays a crucial role in this whole process, ensuring that the features remain distinct and informative as they evolve. And they wrap up this section by explaining how their framework addresses those 2 initial challenges we discussed: maintaining stability amidst significant feature change and handling the complex interactions between different layers.
It's like coming full circle, showing how their approaches successfully tackled the key hurdles they identified at the outset.
To sum it all up, the paper concludes by restating its main finding. P enables deep neural networks to achieve both meaningful, non-degenerate feature learning and guaranteed convergence to a global minimum. They emphasize the crucial link between this preservation of covariance in the induced Gaussian processes and the richness of the learned feature representation. And they suggest several exciting avenues for future research, like extending these findings to more complex architectures, analyzing the speed of convergence, studying generalization to new data, and exploring how OIMP might interact with more advanced training techniques. And in the appendices, they provide all the juicy details for those who want to dive deeper. Detailed experimental setups, results for different activation functions, in-depth explanations of P, and the complete mathematical proofs of their main theorem and supporting lemmas.
It's like they've provided a multi-course meal for anyone interested in deep learning theory. There's something for everyone, from the appetizer of basic concepts to the main course of rigorous proofs and the dessert of potential future directions.
Now, to put all of this in a historical context, it's important to remember that deep learning has had this kind of tumultuous relationship with theory. For a long time, practice was way ahead of our understanding. We were building these incredibly powerful models, but we didn't fully grasp why they work so well.
It was like we were driving a car without knowing how the engine worked. We could get from point A to point B, but we couldn't explain the underlying mechanisms.
And the emergence of this focus on the infinite width limit was a significant step toward bridging that gap. It provided a way to simplify the analysis and start to uncover the fundamental principles governing deep learning.
It's like taking the car engine apart and studying its individual components in isolation to better understand how they interact to produce motion.
And the neural tangent kernel theory was a major milestone in this journey, but it had its limitations, especially when it came to explaining feature learning. It was like having a theory that could explain how to build a house, but couldn't account for the artistry of the architecture.
Or how to bake a cake, but not how to create a truly delicious and unique flavor profile.
Exactly. And PP, as presented in this paper, represents a potential paradigm shift. It suggests that the way we initialize and parameterize these networks is crucial, not only for ensuring convergence, but also for unlocking the full potential of deep learning to learn truly rich and adaptable representations. It's a reminder that the devil is often in the details, and even subtle choices in how we set up these models can have profound consequences for their behavior.
It's a testament to the power of careful analysis and rigorous mathematical frameworks to shed light on the inner workings of these seemingly magical black boxes.
So let's crystallize the key takeaways one more time. P allows features to change significantly during training, unlike NTK, which enables real learning beyond the initial random state. And despite this dynamic evolution, P maintains the diversity and independence of features, preventing them from becoming redundant or collapsing. And the proof relies on this elegant analysis of the covariance structure of Gaussian processes and how this structure is preserved throughout training.
It's like having a self-organizing system that maintains its internal harmony even as its individual components undergo significant transformations.
And the good properties of the activation function are essential for ensuring that this harmony is preserved. And they have the empirical evidence to support all of this, showing that P achieves both substantial feature change and high feature diversity, outperforming other common parameterization methods.
Theory and practice working hand in hand, a beautiful sight to behold.
It truly is. And now, for our segment on novel notions, let's consider some potential future research directions inspired by this work. Keep in mind that the link to the paper is in the description for those who want to dive deeper. One idea that comes to mind is, what if, instead of using a fixed P parameterization throughout training, we explored an adaptive P, where the parameterization could dynamically adjust itself based on what's happening in each layer of the network?
Ooh, an adaptive P. That's a fascinating idea. It's like giving the network the ability to self-regulate its learning process.
Exactly. So imagine you have a really deep neural network with like dozens or even hundreds of layers. It's quite likely that different layers will learn at different rates, right?
Right.
Some might be quick learners, while others might need more time to adjust. And what if we could design a system where the parameterization in each layer could be adjusted on the fly based on how quickly or slowly the features in that layer are evolving?
So it's like having a personalized learning plan for each layer of the network tailored to its specific needs.
And one way to do this could be to monitor those eigenvalues we talked about earlier, those measures of feature diversity. If the eigenvalues in a particular layer start to decrease significantly, indicating that the features are losing diversity, maybe we could automatically tweak the learning rate or the initialization variance for that specific layer to encourage more exploration and prevent feature collapse. And we could do this independently for each layer, creating this like highly dynamic and adaptive training process.
It's like having a team of coaches, each one responsible for a specific group of athletes, constantly monitoring their progress and adjusting their training regimen to optimize their individual performance.
It's a really cool idea, and it could potentially lead to faster and more efficient training, especially for these massive, state-of-the-art deep learning models that are pushing the limits of what's computationally feasible.
Imagine being able to train these incredibly complex models with unprecedented speed and efficiency. That would be a game changer for AI research and development.
Now, for another novel notion. This paper emphasizes the importance of good activation functions for achieving both rich feature learning and stable convergence under P. So this got me thinking, what if we deliberately went against this advice and designed anti-good activation functions? Functions that intentionally violate those carefully defined properties.
That's a bold move. It's like intentionally adding a pinch of chaos to the recipe. What would be the point of doing that?
Well, it would definitely be interesting to see what would happen. One hypothesis is that it would indeed lead to all sorts of problems, like feature collapse or instability during training, which would further validate the importance of those good properties. But there's also this more unconventional possibility. Maybe these anti-good functions could actually be beneficial for very specific, highly constrained tasks where we might actually want feature collapse or a very limited representational capacity.
That's a very counterintuitive idea. Can you give an example?
Sure. Imagine a scenario where we need to deploy a neural network on a very resource-limited device, like a tiny sensor or a low-power embedded system. In these cases, we might need to drastically reduce the size and complexity of the model to make it fit within the device's constraints. And maybe, just maybe, using an anti-good activation function that forces the features to collapse into a lower dimensional space could be a way to achieve this extreme compression without completely sacrificing performance.
So instead of striving for maximum feature richness and diversity, we might sometimes benefit from intentionally limiting the network's expressive power. It's like saying sometimes a simple melody can be more impactful than a complex symphony.
Exactly. And it might even be a way to prevent overfitting, where the model learns the training data too well and doesn't generalize well to new examples. By limiting the capacity of the network, we might actually improve its ability to handle unseen data in certain situations.
It's a fascinating idea that challenges our assumptions about what makes a good neural network. Maybe sometimes less is more.
It's all about exploring the boundaries of our understanding and seeing what happens when we push against the conventional wisdom. So those are just a couple of potential directions for future research inspired by this paper. And remember, these are just speculative ideas, food for thought. Don't go out and start designing anti-good activation functions just yet.
Unless you're feeling particularly adventurous. But always proceed with caution and a healthy dose of skepticism when exploring uncharted territory.
So to wrap things up, this paper has made a significant contribution to our theoretical understanding of deep learning. It provides a compelling argument for why deep networks can be so powerful, showing how a specific parameterization scheme, PIA, can enable both rich feature learning and guaranteed convergence.
It's a reminder that even seemingly subtle choices in how we design and train these models can have a profound impact on their behavior.
And it opens up exciting new avenues for research, both in terms of extending these findings to other architectures and training techniques, and in exploring more unconventional approaches that might challenge our current assumptions.
It's a call to action for deep learning theorists and practitioners alike to continue pushing the boundaries of our understanding and unlock the full potential of these remarkable models.
And for our final thought-provoking question to leave you with, does the success of modern deep learning, even in the finite width networks that we use in practice, implicitly rely on or somehow approximate the beneficial properties of parameterization schemes like P, which have been so clearly demonstrated in the theoretical realm of infinite width? It's a question that might guide us towards a deeper understanding of the true nature of deep learning.
It's a question that reminds us that the journey of exploration is far from over. There's still so much we don't know, and that's what makes this field so exciting.
Thanks for joining us on this deep dive. Until next time, keep exploring the fascinating world of machine learning.
And keep asking those thought-provoking questions. It's the only way we'll ever truly understand the magic of deep learning.